chemical engineering problem. So I would categorize it as a chem example. So propane, we know it is for cooking and heating, right? And we know if we leave propane outside, naturally it will turn into gas. So what's up with the gas? This is its state. I call it state original state or state 0. Huge volume. If I want to transport 1 ton of propane from, let's say, one side to the other side, how many containers would I need to transport this huge volume? It's going to be a lot of containers, right? That's expensive. All right, so what I want to do, as an engineer, I know that if I manage to change this one into something like just this small, maybe even just this tiny. I call it V1. A lot smaller. And we take less containers to transport propane, right? All right, we change state 0 to state 1. Now the question is, how do we do that? What is a process that takes us from original big volume to the desired one, which is smaller, a lot smaller? Whether or not the process exists. Now, let's say all I'm concerned for now is whether or not it exists. Just yes and no. Because, yeah. Because if I say it yes, then I know for sure I'm going to have some gain, right? Gain. From what? From the transportation saving, right? Now, what exactly the process then?
Compression.
Exactly. So, for the sake of simplicity, we'll assume propane behave like ideal gas. And from the ideal gas theory, we have this relation, right? PV equal nRT. Now, a simple process. If we keep pressure constant, we want to increase volume, what we do? We increase temperature. Or, if we keep temperature constant, we reduce temperature. If we keep temperature constant, then we increase pressure. So we have two ways. Either increase pressure, or we decrease the temperature. Now, if I want to build a factory out of this process, then I'm going to reach a chemical engineer and ask him to design me a process that somehow give me the highest efficiency of my factory. So what he's going to do? He first has to figure out like what the process or possible one are, right? What's going to be the one that's doable. And then the cost of the process. We produce a product. There's no free cost product. If we consider the cost of the process as well, and the practical gain would be like the difference between the maximum gain without the cost and minus the cost, right? You need to maximize that difference. So then we have to analyze each particular process. And you know that the cost here actually associated with the energy, right? We know that heat doesn't flow from cold to hot. Water doesn't doesn't fly up from low to high, right? We have to apply something, introduce something, so that the nature goes against its nature. And that something is energy. We need to supply some form of energy to reduce further the heat of the gas. Or we have to apply a mechanical force to compress the gas. So that's a cost. And if he analyzes everything, then he will be able to evaluate the efficiency of the factory. So he has to know the energy flows associated with these possible processes. So let us now stop there and move to the third one, mechanical. So heat engines, very typical, very friendly to mechanical engineers, right? So when we talk about heat engine, the general thing that we think about is what? We supply heat, we get our work, right? So what are we concerned about this thing? about this heat supply and work getting out of the engine process. We're concerned how much work we're going to get out, right? If the work is going to be used to lift things up or to drive a car or shift mode, we'd like to have it as high as possible so that we can lift a heavier load and we can transfer or move further. So heat engine. Now I'm going to use a very simple one, ideal gas engine, which we can simply model by a cylinder and piston system, very simple system, which contain here ideal gas at pressure 1 and volume V1, pressure V1, volume V1. So what it means to have a piston to do a work to environment that we can harvest. Now, first of all, we have to quantify what work is, right? So now from mechanics, we know that work would equal to force times distance, right? We apply a force on a subject, like a move a distance, we create a work. Now, in terms of the piston, force equal to pressure inside the piston and the area of the piston. So it's going to be pressure, area, and the distance. So piston move up or down distance d, right? And if we take this product, it's going to be P delta V. So basically, the piston has to expand, right? It just move up. If we put a load on top of the piston, it move up and lift the load. That's useful work, right? So, and this is by convention, guys. When the system expands, we say it does work to environment. And when it compresses, we say environment does work to the system. It's just convention. And we're going to stick with this one for, again, the sake of simplicity. So now we know that in order to have a work, and we can quantify the work now, which equal to VdV, what should we do for the piston to does a work to environment? We have to change the volume, right? It's just similar to the last example, in which we want to reduce the volume, now we want to increase it. So either we would reduce the pressure or increase the temperature. Like remember, we have ideal gas, so it's going to follow the ideal thermal relation. All right, so in the previous one, all right, let me actually apply it out here. So we start from pressure 1 and volume 1. And now what we'd like to have is we're going to have a bigger volume 2, which can now give us the useful work, right? And we do a very simple process. We keep pressure constant. So how we quantify works here? The work out of this process is going to be pressure 1 times the volume difference, right? This is the work that we're going to get from our heat engine. So what happened here is I imagine you have a piston, you put a load on it, and you heat it up, it lifts the load. And that's that. Now if I remove the load, I want to use exactly the same engine again to lift the second load. What should I do? I have to reset the system back to its original, right, before I can lift the things up. Now what would be the work that I have to introduce back to the system to reset it? Now keeping pressure constant as well. Right? We just move it back to its original position, meaning the volume difference is going to be the same, just opposite sign. So it's exactly equal to the work that the engine produced. Just something doesn't sound right here, right? You have an engine, and it does a work. And it takes exactly the same work that it does in the environment to reset it so that it can continue. What useful that engine is for? Not useful, right? So we need something that actually does a work, that work we can consider as a gain. So how do we do that? Let's say I follow a different process here. I keep first pressure constant, volume constant, and I raise the pressure 2, still volume 1. This is again, follow this PV equal to nRT. This is nothing special. We keep volume constant, and we heat up the system, then the pressure will naturally increase, right? So from here, I keep pressure constant and let the piston expand. Now I allow the engine to do work to the environment. and 3 is exactly volume 2. And from here, I let the system cool down, keeping volume constant, so the pressure will drop back to V1. And from here, it's back to its reset points, right? Original state. I call this state number 1, 2, 3, and 4. So this is where the engine does work to environment. What's the change here? We still have the same change environment, which is V2 minus V1, but the pressure change. Now it changed to pressure 2, which is larger than pressure 1. And this is where we reset the system, right? Exactly the same work. Pressure 1 and V1 minus V2. Now if we take the difference, the gain in terms of work is going to be V2 minus V1 times V2 minus V1, right? All right, so it should be about it. 3 examples. Random maybe, but they do share common thing. Anyone know the common here between the examples? Anyone want to give a try? Yes?
Thermodynamics.
Yes, but can you be more details? In a very simple
Accounting
form.
for energy.
One thing, there's still several things. Do you have a system to study in each?
Equations of state.
Yes, yes. The change of state, the energy flows, but then the energy flows from the system to the environment. It has to be associated with the process, right? If we don't change the environment and the system just at equilibrium with the environment, it won't change the state. So no process happen, the system just be the system. I'm be a healthy man. I don't have to concern about being unhealthy, right? So that's thermodynamics. Thermodynamics is a study about the state of a system. In our example, we do have the system, right? The first one, me myself, is a system. Second one, Ruben is a system. The third one, the heat engine is a system. So it study the change of state of a system. The process that the system takes to change its state and the energy associated with the process. And that's all about thermodynamics. It's just that simple. One single formula applied to mechanical engineering, applied to chemical engineering, applied to something less expected, like our daily events or activities. All right, so this one is a good one, like simple one to remember. But of course, in order to apply this one to a particular case and apply it in an effective way, so this is not enough. We need more details, right? We have to be able to define what are the states of the system, what are the typical processes, any variable describe the change of a state change, so it is a variable, right? Process also has a variable because process itself is the change. So what variable describe the change of a process? And this state is associated with the system and the process is associated with the energies. So now, how can we quantify the energies? Question like this. And energy flows from the system to environment. And we have to concern about the barrier between the system and environment, right? Let's say if our system is actually put in a thermos, it will not exchange heat to environment, right? So we don't have to concern about changing heat. But if we just leave outside, and it will start exchange heat with environment, right? Try to reach some more equilibrium. So we need to know about state, variables, process, variable, how we actually can characterize our system, how it interacts with the environment, and then what energy process or what process, typical one, which is attribute to this system and environment interaction and what energy associated with that and how we quantify this energy. And then in the end, if we want like one thing and the other individually, what's useful is that we need to know how to relate all these variables to all the energies, to all the process, right? Why do we need to relate them? In the end, it turns out we're gonna have a bunch of stuff, and you don't want to remember them all. But we would like to know, or actually in practical, what we would like to do is like instead of measure all these quantities, we just want to measure a few because it's easier, cheaper. And with the relation between them all, by knowing just a few variables, we will be able to derive the rest. So that's how we do engineers, right? So this is actually the structure. And right, so this actually take me to the syllabus. Can you